In this lecture, I'll be talking about subspaces of Rn. Before we get into what a subspace of Rn is, I need to explain what a set builder notation is. This is a notation that's often used to describe sets. In this case, we'll be using it to describe sets of vectors. And it really comes in two different types, and we'll see an example of each of these. A form description describes the form that the elements in the set must have, the form that the vectors have to take. And a property description describes a property that the elements of the set have to have, so a property that the vector has to satisfy in order to get into the set. So for our first example, this is an example of a form description. So this notation here, we've got our curly brackets, and then we've got a colon. So this is the sort of separator. And in between, or on other sides of the separator, before the separator, we have the form that the vectors have to take. And then after the separator, we just have the definition of the variables. So in this case, this tells us that the vectors in this set look like a number, a real number A, in the first component, and then in the second component, 2 times that number A. So examples of elements of this set would be different vectors depending on the value of A. So one example would be if A equals 3, in which case we've got the vector A, 2A, which is just going to be 3, 6. So this is an element of this set that we're calling H. And A could be any real number. So we could have A being the square root of 5, and then our vector A, 2A is just the square root of 5, and then 2 times the square root of 5. So that would also be in our set H. And then again, plenty of other examples. What if A is 0? Well, then our vector A, 2A looks like 0, and then 2 times 0, which is also 0, and that's another vector in our set H. So that's what the vectors in the set look like. That's what the form description tells us. This is a property description. So again, we have our separator in the middle here, the colon. And that just separates the two parts of the notation, doesn't mean anything. And then before the separator, what we have is just a generic vector. This first part doesn't tell us really anything about the vectors in the set other than the fact that we're in R3, right? So this is a set of vectors that all have 3 components. Now, after the separator, we have the property. So this is the rule that the vectors have to satisfy in order to get into the set. In this case, we have to be able to multiply the first 2 components together and get a number that's greater than the third component. Now here, it's a little bit harder to find vectors in this set because we're kind of doing guess and check. But if we do a little bit of guessing and checking, we can find some examples. So for example, we could have 3, 4, 5, and then is this in K? Well, what we have to do is check that. And again, this first number 3, that's my A, the second number 4, that's my B, third number 5, that's my C. So we have to check the property, which is that A, B is greater than C. Well, A times B, that's 3 times 4, that's 12. Is that greater than 5? Yes, it is. So this vector 3, 4, 5 is an element of my set K. So just some other examples. We could have 7, 0, negative 3. Is that in K? Well, we would have to check A, B greater than C. In this case, A times B, that's 7 times 0, which is 0, and C is negative 3. Is 0 greater than negative 3? It is, yes. So that's another example of a vector in my set. So one more example here. We could have, for example, negative 5, negative 2, 0. Is that in my set K? Well, again, I have to check whether AB is greater than C. Negative 5 times negative 2, that's positive 10. C is 0. Is 10 greater than 0? Yes, it is. And so that's another example of vector in my set K. So again, a little bit trickier to generate examples when we're talking about the property description, but that's the idea. Okay, now that we have that under our belt, I can explain to you what a subspace is. So a subspace of Rn is any set of vectors, which might be defined by one of the ways that we just talked about, or maybe in other ways, but it has to have these 3 properties. So the first property, it has to contain the 0 vector, right? So the 0 vector of Rn, remember that's that vector with all entries being 0, that has to be in my set. And then a little bit more significantly, it has to be closed under addition. That means for every vector u and v, every time we pick 2 vectors out of this set, if we add them together, then that sum has to also be in our set, right? And so that idea of if you pick 2 things out of the set and you do this operation, in this case addition, that's what we typically in mathematics call closure. So it's closed under that addition. You can add two vectors in H together, and that doesn't cause you to leave your set H. Similarly, we want our set to be closed under scalar multiplication. Again, if we pick any one vector in this case, any single vector out of our set, and then any scalar, any number, any real number C, and we multiply the scalar by the vector, that result should also still be in our set H. So it has to be able to do these operations, but not have us leave our set H. Okay, so let's go back to that first example. So remember, this was the set of vectors with two entries, where the second entry was double the first entry. And I want us to prove that this set is a subspace of R2. So we've got to check those three things. We've got to demonstrate that this set H has those three properties. Okay, so what were the three properties again? It has to contain the zero vector. So is the zero vector, which in this case is 0, 0, because we're in R2, right? We've got two entries. We want to know, is that vector in my set H? Well, as we saw earlier, if A is 0, well then A2A, that's 0, 0, and that is in H, so that checks. So we've got one of our three properties checked. We're good to go with that one. Now we've got to check the other two. The second property we have to check is this set closed under addition? Okay, so the closed under addition property says if you take any two vectors out of my set H and add them together, I get another vector in my set H. So let me demonstrate an incorrect approach here. Right, so this is a common approach that a lot of students tend to take, and I just want to demonstrate why it doesn't work. What a lot of students will do is say, well, I can just pick two vectors, how about 5, 10, and -3, -6, and I can add them together and see what I get. That's not going to work. Because even if you do that addition and see that you get a vector that's in H, that doesn't prove that the set is closed under addition, because closed under addition means no matter which two vectors you take, if you take any two vectors and add them together, you should get a result that's in your set H. And just one example doesn't show that. So what we have to do is do this in the abstract. We've got to show that no matter what two vectors we take, we get something that's in H. Okay, so the way that we do this is we start by saying, let's let vector U and vector V be in H. And these are going to be generic H vectors. So by the definition of H, right, by the way that this H is defined, which is this over here, by the definition of H, we know what U and V look like, right? This is a form description, and the form description tells us what the vectors look like. So this means that U looks like A2A, and V looks like A2A. Wait a second. If we do that, if I write that, well, then that would imply that these two vectors are actually the same vector, right? Because it's the same A in both places. So I don't want to do that. So what I do for the second vector is instead of calling it A, let's give it a different name. Let's use a different letter of the alphabet. How about B? So U is A2A and V is B2B. So they have the same form, but they probably aren't the same vector. If I pick two vectors out of this set, I probably don't pick the same vector twice. So I would say for some real numbers, A and B, right? And because A in this case is coming from the real numbers. Now that I've got two generic vectors out of this set H, now I can add them together and see if what I get is an element of H. So now what I do is add them together. So now U plus B, if I add them together, I get A plus B, 2A plus 2B. Is that in H? Well, what do you have to do to get into H? Well, what you have to do is you have to be a vector where the second entry of your vector is 2 times your first entry of your vector. And we have that here, right? And we can show that, we can make that a little bit more clear by rewriting this, doing a little bit of algebra, and rewriting this as A plus B, and then 2 times A plus B. And so that's clearly in H, and so we're done there. Okay, so we've got 2 out of 3, right? So this proving something's a subspace, we've got a lot of work to do. So we've gotten our first property, our second property. Our third property is that this has to be closed under scalar multiplication. Okay, so when we said we wanted to show that this was closed under addition, we said let's pick 2 vectors in H. For scalar multiplication, we're going to pick 1 vector out of H and an arbitrary scalar. So we're going to say let's let U be in H and C be a scalar. And just like before, we don't want U to be any particular vector. We want it to be a generic vector that's coming out of our set H. By the definition of H, what does U look like? U looks like a 2A for some scalar A. And now what we want to do is make sure that when we take this vector U and multiply it by C, what we get is an element of H. So we do that algebra. So CU is C times the vector A2A. That's the vector CA and then 2CA. But that is a vector that looks like a real number and then 2 times that same real number. And that's clearly going to be an H. So that works out as well. So use this example as a model for your problems that you work on. So when you get a problem to do on your own and you have to prove that something given in this sort of set notation is a subspace, follow these 3 steps and try to write it up in the way that I've done it here. Okay, let's go back and look at that example 2 that we looked at. So remember, this was a property description. So again, the difference here is that what this notation is telling us is not the form that the vectors have to take, but a property that the vector has to satisfy in order to get into the set. In this case, we call it K. And now I'm asking actually a harder question. I'm not telling you what to do. I'm asking you a question. Is this a subspace? And what we have to do to justify whether it is or isn't is different, depending on whether our answer is yes or no. If we think the answer is yes, then what we would have to do to justify that answer is just what we just did in the previous example. We would have to go through those 3 properties and prove that this set K contains the 0 vector, is closed under addition, and is closed under scalar multiplication. But if we think the answer is no, then all we have to do is show that one of those 3 properties doesn't work. We either have to show that this set doesn't contain the 0 vector, or that the set is not closed under addition. Showing that the set was not closed under addition would mean finding 2 specific vectors. So we can, in that case, find an example, a counterexample is what we call it, an example of 2 vectors in K that when we add them together, we end up not in K. Or we could show that the set is not closed under scalar multiplication, which again would mean coming up with an example vector from K and an example scalar, and showing that when we multiply that scalar by that vector, we end up not in K. So showing that the answer to this question is no is much less work because we can use examples and we only have to look at one of the 3 properties. If one of the 3 properties doesn't work, then the whole thing falls apart and the set is not a subspace. So if we look at the first one of those properties, so remember that first property was the 0 vector. Is the 0 vector 0, 0, 0 in K? Well, remember what we had to do to check whether a vector was in K. We had to check this property, A times B greater than C. So A times B greater than C would be 0 times 0, is that greater than 0? Well, that would say 0 greater than 0, but 0 is not greater than 0. If that said greater than or equal to, we'd be in business, but it doesn't. It says greater than. So that doesn't work. And so that means that right away we're done. We know that no, K is not a subspace. So how about another example here? Let's look at R2. So typically we think of R2 as kind of like the XY plane, and then R3 is kind of like XYZ 3-dimensional space. And so typically we would think of the XY plane as kind of living inside of R3. But it doesn't really, because the vector space R2, that's vectors that look like XY. And the vector space R3, that's vectors that look like XYZ. So if you have your vector with 2 components, that isn't actually a vector in R3. It doesn't have a 3rd component. So it's not even really a subset. However, there is a copy of R2 that lives inside of R3. The XY plane is all of the vectors with a 3rd component being 0. And this is a subspace. And again, we could prove that this is a subspace using the method that we used back in example 1. Here's another example. If we have a line that does not pass through the origin, this is going to be not a subspace of R2. And remember, to show that something is not a subspace, we just have to look at one of those 3 properties. But it turns out that this line doesn't satisfy any of those 3 properties. So the first property is that the line has to contain the 0 vector. But of course it doesn't, because the line doesn't go through the origin. And so the first property of does this contain the 0 vector would be no. And we could stop there, But just as an illustration, I want to show you that actually the other two properties don't work either. So if we said closed under addition, so what does it have to do to be closed under addition? We have to be able to take any two vectors in this line. So maybe there's one vector and there's another vector. And if we add those two vectors together, we get our little parallelogram. We add our vectors together. We get this vector over here, but this is not on the line. And so that means that this set is not closed under addition because we took two vectors in the set, added them together, and got something that wasn't in the set. What about closed under scalar multiplication? Well, for that, we have to be able to take a vector in this set, multiply it by a scalar, and have to remain in the set. So if I took a vector, let's say this vector up here, and let's say multiplied it by 2, well, if I multiplied it by 2, I get a vector that points in the same direction, but is twice as long, and that gets me way over here. So let's say if that's v, and this is 2v, that's not going to be in my set either. And so this line spectacularly fails the subspace tests. It doesn't satisfy any of those three properties. So a general way that we often find subspaces, that we generate subspaces, is by taking the span of a set of vectors. So what this theorem says is that if we have any collection of vectors in Rn, right? So P here is the number of vectors that we're talking about. So if we have P vectors, which could be one vector, it could be 17 vectors, we don't have any idea. And then what we say is the span of that set of vectors. So remember here, this is the set of all linear combinations of those V's, V1 through Vp. Then that set, that big set of lots and lots and lots of linear combinations, is a subspace of Rn. Okay, so how would we prove that? Well, as we've done before, back in example 1, we have to do 3 steps. We have to prove that this set of vectors, this set of linear combinations, satisfies all 3 properties. So the first property is the 0 vector. So is the 0 vector part of this span? Well, the 0 vector is a linear combination of those v vectors. Even though I really don't know anything about these v vectors, what I could certainly do is put the scalar 0 in front of each of them. That is a linear combination, that counts. And so that is in H because H is the set of everything that looks like that, every linear combination of these v's. For the second step, we have to show that this set is closed under vector addition. What that means, again, is that we have to be able to take any 2 vectors out of this set, add them together, and make sure that we get another vector in this set. So we start by saying let u and v be vectors in H. What do we now know about u and v? Well, not much, but what we know is that u and v are in this set H, which is the set of all linear combinations of those v vectors. So that means that u is a linear combination of the v vectors, c1v1 plus c2v2 plus cpvp for some scalars ci. Again, I don't know what those scalars are, but they have to be there because that's what a linear combination is. And v also looks like that, but with probably different scalars. So d1, v1, same vectors, but probably different scalars. d2, v2, all the way up through dp, vp. For some scalars di. And now what we want to do is add these together and find out whether or not we actually end up still in H. So we would say now, we write u plus v, and we say, okay, what the heck is that? Well, if we take c1v1 plus d1v1, by our algebraic properties, we can write that as c1 plus d1 all multiplied by v1. So I'm using a distributive property there, but I can do that. So this is from what I wrote in the green box there. And then these 2 vectors added together, I can do the same thing. c2 plus d2 all multiplied by v2. And I can keep doing that all the way up through cp plus dp all multiplied by vp. Now, why am I doing that? Well, I'm doing that because if we look at what we have here is a linear combination of the v's. because that's what a linear combination is. Scalar times the first vector plus scalar times the second vector plus, all the way plus a scalar times the last vector. And that's what H is, that's what this span is, and so this vector is in H. So pretty abstract, a little alphabet soup going on, but hopefully that makes sense. Finally, going to be pretty similar to part 2 here. We have to show that this set is closed under scalar multiplication. So again, since U is an H, by the definition of H, U is going to look like a linear combination of these V vectors. So C1, V1 plus C2, V2 plus CP, VP for some scalars Ci. Again, we don't know what those scalars are. We don't want to use specific numbers there because we don't know what those numbers should be. And then we've got our scalar C. So now what we want to check is that when we multiply C times U, we want to see what we get. Well, that's going to be C times that linear combination, C1, V1, C2, V2, all the way up through CP, VP. And now we can distribute. So I've got C, C1, V1, plus C, C2, V2, all the way up through C, CP, VP. But now I can be a little bit clever with algebraic properties again. This time I'm going to use our sort of quasi-distributive law, which lets us take the two scalars and multiply them together. That's a sort of associativity, not really quite associativity, but that's one of our algebraic properties that we talked about before. And this, again, is a linear combination of the V's. And so that's in H because that's what H is. H is the set of all of the linear combinations. So if we have a linear combination of the V's, then what we have is a vector that's in H. So we've got two more important subspaces to talk about, but they're sort of boring, but they are important. They're going to come up as we keep studying our vector spaces here. So the set that just contains the zero vector, very small set, only has one vector in it, but it counts as a subspace. So remember our three properties. The set has to contain the zero vector, but of course this set only contains the zero vector, so it kind of gets that one for free. It has to be closed under addition. But again, what this means here is that if I take two vectors out of my set, so if we say let U and V be elements of this set that just contains the zero vector, well then U would have to be the zero vector, and V would have to be the zero vector, right? That's the only thing we can pick. We don't have any choices. There's only one thing in this set. And the zero vector plus the zero vector is the zero vector. Similarly, to show that this is closed under scalar multiplication, if we pick a vector out of this set, the only thing we can pick is the zero vector. And if we multiply the zero vector by any scalar, we just get the zero vector again. So there's not really much going on there, but again, this does count as an example of a subspace that we will encounter as we keep studying this stuff. Another sort of boring example, kind of on the other end of the spectrum, is the set of all possible vectors. So Rn, this is just all vectors with n entries. So does that contain the zero vector? Sure. The zero vector is part of the set of all vectors. So again, we get that one pretty easily. Is this closed under addition? Well, if I take two vectors with n entries and add them together, adding vectors doesn't change the number of entries they have. So yeah, that's going to have n entries as well. Is this closed under scalar multiplication? Again, yes, because if I take a vector with n entries and multiply it by a scalar, that's not going to change the number of entries it has, so we're still going to have n entries. So again, we get that this is a subspace. Okay, to wrap things up, what we're going to be doing with this generally is looking at two important subspaces associated with a matrix. And these are called the column space and the null space for that matrix. So we're going to study these subspaces coming up, and then we're also going to look for how to find what we call a basis for a subspace, which is a useful way of understanding which vectors are elements of that subspace. It's a specific way of describing a subspace. So that's what's coming up.